So in chapter 9, we're going to be talking about relations and functions. And so this first section just gives us an kind of an introduction to what both of those things are and how to identify them. So let's go ahead and start off with a definition of both. So let's start off with a relation because a function is a specific type of relation. So we need to know what a relation is. So a relation is just any set of ordered pairs. So you can think of it kind of like a line, because the line is a bunch of ordered pairs. A line is also most of the time a function, and we'll talk about why that is. An example of a relation is, so because it's a set, we're going to use curly brackets. And then it's a set of ordered pairs. So we're just going to have a list of ordered pairs here. Let's say we have the ordered pair 0, 0, 1, and 3, 2, 7, and 3, 10. So we have a set of 4 distinct ordered pairs here. So that's all a relation is you're going to have a set of ordered pairs. And now a function. Now to define a function, we're going to use a relation. So a function is a relation in which, and now this is the part that sounds kind of weird. So let me write it out and then we'll kind of talk about it. So for each value of the first component, and so in most cases that's the x. So the first component of the ordered pairs of the relation So for each value of the first component, there is exactly, and this part's important, it's exactly, not at least, one value of the second component. Now, what does this mean? How can we say this in some other ways that might make a little bit more sense? One way I'll usually describe this is that every x has exactly one y. So we'll take a look at some examples of things that are functions and things that are not. Another way is to think of this, because we're not always dealing with x's and y's. Every input has exactly one output. And a really common example of this is like a vending machine. So if you have, a bunch of buttons on a vending machine, you're looking at, I don't know, let's say it's a soda vending machine, and you push a button for Coke. You don't want to push that button for Coke, and then sometimes you get Sprite, sometimes you get Pepsi, sometimes you get Coke. You want to push that button for Coke and always get Coke every single time. So that Coke button has exactly one output, and that should be Coke. So that would be a function. That means that the vending machine is functioning properly. If it were not functioning properly, then sometimes you would get other sodas that are not Coke. So that's an example of something that is a function. That's just kind of like more of like a real life example. But that's one way you can think about a function besides ordered pairs. Now for this, let's actually cover 2 more definitions really fast before we talk about some examples. Our next definition is domain. And so domain is something that we have kind of seen before, but not in the sense of functions. So the domain is the set of all values of the independent variable. Ooh, I did not spell that right. Independent variable. And in most cases, that's going to be x. And then the range is the set of all values of the dependent variable. And as you can probably guess, that is our y most of the time. The way I remember this, which one is domain and which one's range, D comes before R in the alphabet and X comes before Y. So that's the way you can kind of remember those. Most of the time we'll be talking about domain because domain's a little bit easier to find from an equation. And so we'll see that a little bit more at the end of the section. But we are going to find domain and range for some sets of ordered pairs. So let's go ahead and look at some examples. Yeah, we'll start them here. So for these examples, we're told to determine whether the relation defines a function, because all of these we're going to look at are relations. We want to figure out if it's a function, so if it's functioning correctly. And then state the domain and range. So we can always state the domain and range. It doesn't have to be a function. And you'll see some of these more in your homework. For this first example here, we're given the set of ordered pairs 0, 3, -1, 2, and -1, 3. So first thing we're going to do is figure out whether or not it is a function. Well, if we go ahead and look at our definition again, we want to make sure that every x has exactly one y. Now what we're going to do is we're going to look at our x values. We have a 0, which goes to a 3 here, and we don't have any other 3 or zeros for x's. We only have a -1 and a -1 here. So that one's good. If we take a look at the second point, we have a -1, which goes to 2, but we also have a -1 that goes to 3. So the problem here is that this x value of -1 has 2 different y values associated with it, which means that this is not a function. So in general, if you see any x values that repeat themselves and they have different y values, make sure they don't have the same y value there, then it is not a function. So we can't have repeating x values. All right, now let's find the domain and the range. So the domain is the set of all of the x values. So now all we're going to do is list out the x values. So I'm going to use curly brackets. We have a 0, a -1, and a -1. We don't want to write any doubles, so we're just going to have 0 and -1. And now for our range, this is all of the y values. We're going to have 3, 2, and 3. Again, that 3 repeats itself, so let's just put 3 and 2. Oops. Make sure that is a curly bracket at the end. Now notice that I didn't put these in numerical order. That's kind of standard notation, so we should have -1 and then 0, and then 2 and then 3, but it doesn't matter. These are still correct. As long as you have your domain and range values written out, it doesn't actually matter what order you put them in. All right, let's go ahead and try a couple more of these. Now that you've seen one, I would try to do the next one by yourself. So this one, we're given the set of ordered pairs 2, -2, 4, -4, and 6, -6. So again, if we want to figure out if this is a function, we're going to look at our x values. First, we have a 2, a 4, and a 6. Now we have 3 distinct x values, So each x value is going to its own y value. So 2 goes to -2, 4 goes to -4, and 6 goes to -6, which means every x has exactly one y. So this one is a function. And let's just say every x has exactly one y. Remember that this has to be exactly one y, not at least one y. They will have some answers on your homework where that'll be the only difference. They'll have exactly and at least. So make sure you're paying attention to the language there. Now let's look for our domain and range. Remember, domain is the set of x values. So domain is 2, 4, and 6. And our range is the set of y values. So what is our range? Well, it's -2, -4, -6. And none of those repeat, so we don't have to worry about getting rid of any of them. Okay, let's go ahead and try another one like this. This next one, we're given the relation only has 2 points, -1, 5, and 0, 5. So this one is one that will sometimes trip people up because if you notice this y value has been repeated, but if we take a look at our x values, we want every x to have exactly one y. So -1 goes to -5 and 0 goes to -5. Notice how we don't have any x's that go to more than one value. If we had also had, let's say, -1, 6, that would mean we'd also have -1 going to 6, as well as -1 going to 5. But because we don't have any repeating x's, we might have repeating y's, and that's perfectly fine. This one is a function. So repeating y values are okay. And now for our domain and range, see if you can write these two out. So remember, domain is the x values, range is the y. So domain is going to be -1 and 0. And the range is 5 and 5. Those are the same, so we'll just write it once. So the range is just one single value, but you're still going to put it in those curly brackets, which on my math app, they will already have those written in. You'll just be filling in the numbers on the inside. So make sure you don't write those curly brackets in there twice because it will mark you as wrong, unfortunately. So just keep an eye on what they have already put on the answer for you. Okay, so those are a couple different relations, but all of them had the same kind of appearance. They were given to you as points in a set. We can also see relations given to us in a slightly different way. So for this one, we're given, it's going to look kind of weird. So we're going to have a list of x values on the left. So we're going to have 1, -2, and 3. Those are going to be in a circle. Then on the right, we're going to have 2, 4, -1. Those are in a circle. And now we're going to draw lines from each x to each y, depending on where it goes. So they have a line from 1 to 2, from -2 to 4, and from 3 to -1. And it doesn't always have to go directly across. We'll see another one that doesn't go directly across. But what this is saying is they're basically giving us ordered pairs here. All of the values on the left are x's. The values on the right are y's. And so this is saying that x an x value of 1 has a y value of 2. So you can think of that like the point 1, 2. The next one, we have -2, which goes to 4. So that's the point -2, 4. And then the point 3, -1. So if we want to figure out if this is a function, let's see if we have an x that goes to more than one y. Now this one is actually pretty nice to tell, because if we look at the arrows, this x value of 1 just goes to 2, x value of -2 just goes to 4, and x value of 3 just goes to -1. So every x only goes to one y value, and so yes, it is a function. We'll take a look at one that isn't, just so you can kind of see that. And then the domain and range, these are also super nice because the domain are the x values that are listed over there on the left. So 1, -2, and 3. And the range values are on the right. So 2, 4, and -1. You could also see something like this drawn as a chart. Just in case you guys see this, you'll have the x's on the left, so 1, -2, and 3. And then on the right, you'll have 2, 4, and -1. These ones, you don't need an arrow. You're not going to see arrows on this one. This just means the point 1, 2, -2, 4, and 3, -1, just like you've seen XY tables before. All right, let's take a look at one more of these so you can see what one of these looks like when it is not a function. So number 5, again, we're given these circles of numbers. So 4, -2, on the right, 1 and 0. And we're going to have an arrow from 4 to 1, an arrow from -2 to 0, and an arrow from -2 to 1. Now, they have given us 3 different ordered pairs, which you can tell based on the number of arrows. They've given us the point 4, 1, -2, 1, and -2, 0. So this one is not a function. The way you can tell is that this -2 right here goes to -1, and it also goes to 0. Remember, each x can only go to one y. This one goes to 2 different y's. So this one is not a function because that x goes to 2 different y's. And let's figure out our domain and range. Again, domain and range are super nice from these circles here. Domain are the x values on the left, so 4, -2. And the y values, the range, are the numbers here on the right, so 1 and 0. Okay, so that's figuring out domain and range and whether or not something is a function from a set of ordered pairs. Now we can also determine if something is a function based on a graph. And so we're going to use something called the vertical line test. And it's exactly like it sounds. We're going to be using a vertical line to figure out if something is a function. So what we're going to do is we're going to use this little description here to figure out if something is a function, and we'll talk about why this works in a second when we look at some examples. So let me write this out and then I'll kind of talk about what this means. So if every vertical line intersects the graph of a relation in no more than one point, then the relation is a function. So the way that this is written, this is how it's written in the book, sounds kind of complicated. The way I like to think of this is that if a vertical line crosses the graph more than once, then the relation is not a function. So what they did was they said that something is a function if the vertical line intersects the graph at no more than 1 point. So it can only cross the graph at 1 point. What I do is a little bit different. It's actually the exact same thing. It's just kind of said backwards. So if it crosses at more than 1 point, then that relation is not a function. So let's look at some examples to kind of see what we mean by this. And this first one is a set of ordered pairs, but these ordered pairs are drawn on a graph. And again, I'm sorry for my graphs not being super pretty without graph paper. So we're told to determine whether the relation is a function and state the domain and range. Now, this first one's really similar to what we've been looking at, actually. So let me go ahead and draw this graph out. So we're going to have our vertical axis, horizontal axis, and I'm going to put some points on there. So we're going to have the point -3, -1, so left 3, down 1. The point -2, 2, so left 2, up 2. The point 2, 3, so right 2, up 3. And the point 3, -2, so right 3, down 2. Now, this is a graph because we've plot the points on a graph. It's not a graph in the sense that we have these points being connected, which is perfectly fine. What we can do though is we can figure out if this relation is a function using the vertical line test. So what the vertical line test says is that if we can draw a graph, or sorry, if we can draw a vertical line and it passes through the graph at more than 1 point, then this is not a function. If I draw a vertical line through this point here, that only goes through this 1 point, so that one's good. Same thing here, if I draw a vertical line here, it's only passing through this 1 point. Same thing here, passes through 1 point. Same thing here. So we only have these 4 distinct points and none of them lie directly above one another. So remember, we're drawing vertical lines, not slanted lines. So this one is a function. Because a vertical line only passes through 1 point. No matter how many times you draw that vertical line in, it'll only ever pass through 1 point. Now, the way to think about this in comparison to what we were looking at before, remember before we were saying that each x can only have one y value. Well, if we look at the x value of -3, this only has a y value of -1. There are no other x values of -3. Same thing at -2, we only have a y value of 2. For x equals 2, we have a y value of 3. And for x equals 3, we have a y value of -2. So each x only has one y. So it's the same kind of idea. The vertical line test is just more helpful when we're looking at graphs. All right, now the domain and range, and this one's nice because this is like we've already seen. For the domain and range here, we're just going to list out the x and y values. So the domain is going to be -3, -2, 2, and 3. So -3, -2, 2, and 3. And the range is the y values, so -1, 2, 3, and -2. Now, those ones were pretty similar to what we were just doing. So let's take a look at some examples that are actual graphs. So we're going to be continuous lines. Number 2, and I'm going to kind of roughly draw this graph out. The important thing here, there's going to be a couple of important parts. One important part is the shape. And the other important thing is that it goes through this -2 right here. So it's going to be this kind of sideways U or this C shape that goes like this. Doesn't have to be perfect, just make sure it goes through -2 on the x-axis. And I actually don't care what these y values are right here. So now to determine if this is a vertical line, or sorry, if this is a function, we're going to use the vertical line test. Now, if I were to draw a vertical line over here on the left, even though it doesn't really look like it, this is only passing through at one point. So at that one point, or sorry, at that one vertical line, it's only going through one point. But if I were to draw a vertical line over here, we pass through 2 points. That means that we have an x value that has 2 different y values associated with it. And so this is not a function. So if you can draw a vertical line anywhere on the graph and it passes through 2 points, it is not a function. It doesn't matter if you find a vertical line that only passes through 1 point. We care about that one case where it passes through 2 points. Now, our domain and range are a little bit trickier here. So the domain, again, is all of the x values. And because we have an infinite number of x values, we want to go based on the first x value or the smallest x value to the largest x value. And we're going to do these in interval notation because we have a whole in an infinite number of x and y values here. So whenever you don't have distinct points, if you have a line like this, you're going to want to use interval notation. So the furthest left that we go in terms of the x values here is -2. So because we have an actual point there, we're going to have -2 with a bracket, comma, the furthest right that we go, well, these arrows mean that we're going forever to the right. Since we never stop, the furthest right we go is positive infinity with a parenthesis. Think of that just like finding the interval notation on a number line. Furthest left, furthest right. Now with the y values, to find the smallest y value, we're going to find the lowest we go and then the highest we go. This one looks kind of weird because if we look at these arrows here, it looks like they're kind of leveling out. But whenever you have a graph that is shaped like this, these actually go down forever. And they're going to keep going down forever. It'll be gradual, but it will eventually make it to -infinity. So our lowest value is -infinity, and the highest we go, this is also going to go up forever. So we're going to go up to positive infinity. Anytime you see those arrows, it's always going to go forever in that direction. So forever up to the right and forever down to the right. Now let's look at a couple more examples of these so you can see some other domain and range examples. So our next graph here, let me go ahead and draw this one out. For this one, again, I'm just kind of roughly sketching it. The most important part here is that you have that it starts in the middle there. So it starts right there at 0. Whoops. And it also goes down to the right. So we're going to have this kind of upside down V shape. Let me put some tick marks on the graph here so you can kind of distinguish between the two, the axes and the graph. So we have this upside down V shape, which is an absolute value function. It's something you'll see in Math 126. And so we might actually see it in 96 a little bit. This is kind of where they're introduced, but we're not going to be graphing them a whole lot. So for the purposes of this section, it doesn't matter if you know what kind of function this is. All you need to be able to do is look at this graph and use the vertical line test to see whether or not this is a function. So is it possible for us to draw a line and for it to go through 2 points on our V-shaped graph here? Well, no. If I were to draw one, let's say right in the middle here, it only goes through this 1 point. If I drew one over here, just goes through 1 point. Over here, still goes through just 1 point. There aren't any kind of overlapping vertical points like we had here. So this one is a function. And now for the domain and range, so the x and y. Remember, the x goes left and right, the x-axis, so we want the furthest left that we go and the furthest right. So notice how our graph goes forever down to the left and forever down to the right. That means that the furthest left we go is negative infinity. The furthest right we go is positive infinity. So our domain is negative infinity to positive infinity. And our range, we want to go from the least to greatest. So the furthest down we go, well, these lines go down forever. So this lowest value is also negative infinity. But what is the largest y value that we have if you go up? The largest y value we have is right here. And the y value right there is 0. So we go up to 0 with a bracket. You're always going to have brackets in this class on those distinct numbers. On the infinities, you'll always have parentheses. All right, let's go ahead and try one more of these before we get to the last part of our section. So for this one, again, we'll have our graph drawn out. And we're going to have this kind of almost S-shaped graph. So I'll just do this one. Let me do these tick marks first. Doesn't matter where those are. There's not actually any distinct points that we care about on this one. We're going to have this line that goes kind of like this. So kind of S-shaped. This would be from a cubic graph, so something like x cubed, which again doesn't matter for this class, but just so you're familiar with it. Now, let's go ahead and figure out if we can draw a vertical line that goes through more than 1 point. So see if you can figure out if this one is a function or not. And if we go ahead and draw a vertical line, if I draw it, let's say right in the middle, it only goes through 1 point. All the way over on the left, it only goes through 1 point. Same thing over here, only goes through 1 point. Even though it looks like it's getting really straight here, this will never go completely vertical. So this is just going to go out to the right forever. So this one, because we can only go through 1 point, is a function. And if we go ahead and look for the domain and range, Domain is the x, range is the y. Domain, so furthest left and furthest right. So furthest left we go, even though it doesn't look like it, this goes out forever to the left. And if we follow it up, it goes out to the right forever as well. So what is our domain going to be? Well, forever left and forever right means negative infinity to positive infinity. And now for our range, this is going to go down forever, and it's also going to go up forever, which means our range is also negative infinity to positive infinity. So that means that every single y value occurs at least once on this graph, as does every single x value. It might take a while to cover all of the x values, but it'll eventually happen because this is going to go forever in both directions. All right, so that's the vertical line test. Now the last part of this section is kind of a weird set of examples. We're not going to spend a ton of time looking at these. I'll give you kind of a hint for how to do these in your homework. The most important thing for these questions is going to be the domain. So let me write out what we're going to be doing. So for this set of examples, we're told to determine, and I'm sure you can guess what we're going to determine. We want to determine whether the equation, this time we're looking at an equation, not a graph, represents a function. And then state the domain. So when you're looking at an equation, it's not too bad to figure out what the domain is. Range is a little bit harder. So we're just going to focus on the domain. And all of the ones that you're going to see in your homework will represent a function. So I'll tell you that ahead of time, but I do want to show you kind of why that is. So number one here, we're given y equals 6x plus 12. Now, hopefully you recognize this equation. This one is linear. So what we're going to do is we want to figure out if, going back to our definition of a function, every x has exactly one y. So if there is any way for us to plug in an x and get two different y values, then it is not a function. But if we plug in x, let's say x equals 1, we would have 6 times 1 plus 12. And no matter how many times I plug in 1 here, I'm always going to get 6 plus 12, which is 18. There is no way to get multiple y values with each x value. Because the way that multiplication works, because we're doing 6 times x, multiplication is only ever going to give you one answer. If it gave us two answers, then order of operations would be a lot messier because we would have multiple answers all over the place. But when we take a number, multiply it by 6 and add 12, we can only get one answer. We can't get 18 and negative 18. We can't get two different numbers. So this one is a function, and all of these will be. And now for the domain. Now for domain, when we're looking at equations, we want to find the values. Instead of listing out all of the values that x could be, because there's a lot of different values, we want to find the values that x cannot be. Now this is kind of like the restricted values we talked about in chapter 7, if you remember those. Now for a linear equation, I could plug in a negative number for x, I could plug in 0 for x, I could plug in a positive number for x. There's no restrictions on what I can plug in for x here. So that means our domain is all real numbers. And as an interval, we write that as negative infinity to infinity. There are no restrictions on x. All right, let's take a look at another one. This next one, we have y equals x to the third power. Now again, for this one, if I think about plugging in, let's just try plugging in 1 again. We would have 1 cubed, and 1 cubed is 1 times 1 times 1, which is just 1. There's no way to get a different y value, no matter what x I plug in. Even if I plugged in -1, -1 cubed is always going to give me -1, which means this is a function. And this is just because this is how operations work. We'll see one example, which won't be on your homework, but I do want you guys to see one that is not going to be a function. And then our domain, again, we've already seen that I can plug in positive values. We can raise any number to the third power, including positive numbers, negative numbers. I could take 0 and raise it to the third power. We would just get 0. So there's no restrictions, and we get -infinity to positive infinity. This will not always be the case. This is just the case for these two. Let's go ahead and try another one. So this next one, we're given y equals 3 over x. Now, again, for this one, if I plug in a value for x, is there any way for me to get multiple y values? Well, if I did 3 over 1, that would just give me 3. If I did 3 over -1, that gives me -3. Since we're using division, there's no way you can get more than one solution. So again, this one is a function. And our domain, this one we do have to be a little bit more careful with, because this is one of the rational expressions we were looking at back in chapter 7. Remember, when you're looking at this, what number can we never divide by? We can never divide by 0, which means that our denominator, in this case is x, cannot equal 0. There's no solving to do here. So we're going to say that x cannot equal 0. But for our domain, the domain's a little bit weird for this one because we want to write this as an interval. And so as an interval, if you think of this on a number line, I'll do this over here. If we have 0 right here, I can have everything to the left of 0, everything to the right of 0, but I cannot include 0 itself. So you can think of a parenthesis going this way, a parenthesis going this way. So you can get as close as you want to 0, but you can't equal exactly 0. So if I write this as two distinct intervals, we're going to have everything from -infinity to 0 with a parenthesis union everything from 0 to positive infinity. That's the way you kind of exclude a single number from your domain. Now let's look at one more example. For you guys to write down, the last one will just be kind of showing you when we don't have a function, just so you know that they do exist. Number 4, make sure you write this one down. So this one we're given y equals 2 over x plus 2. And as you can already guess, hopefully, this one is a function. There's no way we can plug in an x value and get multiple outputs because we're adding and then dividing. Those both only give us one answer. So this one is a function. And now, if we figure out our domain, the domain here, just like we did in the last one, we want to find what x cannot equal. That's a lot easier than finding what x can equal initially. And so remember, with a fraction, we cannot have 0 in the denominator. So we're going to take our denominator and say that this cannot equal 0. Now, if I solve for x here, we get x cannot equal -2. Now, instead of going through and looking at the graph for this one, let's just go back and look at what we did last time. Because we said x could not equal 0, we had everything to the left of 0 and everything to the right of 0, and then we put the union in between to join those two together. So again, we're going to have, everything to the left of -2, so from -infinity to -2, parenthesis, union, everything from -2 to positive infinity. So this is going to give you everything to the left of -2, to the right of -2, but it's not going to include exactly -2 because of those parentheses. Now, for this last one, you don't have to write this down if you don't want to. This won't be on the homework, but I do want to show you one example that is not a function. So this one, we're given y is less than or equal to 4x. So this one is actually an inequality, and this is not a function because let's say I plug in 1 for x. So we did 4 times 1, and that would give us 4. But now the y values are less than or equal to 4. So any y value that is less than or equal to 4 is going to satisfy this inequality. So a y value of 2 would satisfy this inequality. So would 1 or 0 or anything less than that, and all of the fractions in between. So whenever you have an inequality like this is not a function. And then the domain, because it's an inequality, linear inequality, our domain is -infinity to positive infinity. All right, so there is one last little example I want to show you just as kind of a hint for your homework. So let's go ahead and get a new page here. So for your last homework problem, you're going to be given some data. So you're going to be given a chart with some data in it. There's going to be some numbers here on the left. It'll be like 94, 79, 85, and so on. Some data over here on the right, say 6, 18, 7. Your chart's going to be a little bit bigger than this, but this is going to be some kind of data. So you're going to have percents of something over here, and I'm leaving these off because this is really the important part, at least for understanding this problem. So you're going to have some other percent over here. Those are just the labels of what these data points mean. But part A of the problem is going to ask you to write this data as ordered pairs. So to write this as a set of ordered pairs, you're going to have your curly brackets, and they should give those to you. And so our ordered pairs, we're just going to look at each row in our data table. We're going to have 94, 6, and so you're going to put 94, 6, comma, our next ordered pair is 79, 18. And make sure all of these ordered pairs are in parentheses. And then our last one we have is 85, 7. So that's the kind of thing you're going to be doing in part A. And then part B and C is exactly like what we've seen. So part B, it's going to ask for the domain and range. So remember, domain are all of the x values. So in this case, your x values are 94, 79, and 85. And as you can probably guess, our range is 6, 18, and 7. And then lastly, part C is going to ask if it is a function. And so based on what we talked about in the very beginning of this section, as a hint, check to see if each x has exactly 1y. So that's what you're going to do for that last part. And there's just one word problem on there, so it shouldn't be too bad. And then for the rest of chapter 9, we're also going to be looking at some functions, some function notation.